Let's take a look at this problem, taken from the Asian Pacific Maths Olympiad 2012. It says, find all primes p and positive integers n such that n to the p plus 1 divided by p to the n plus 1 is an integer. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. This is a very beautiful problem to me because the statement is very short, very concise, and the expression given is very beautiful, it's very elegant, because the top part and the bottom part are almost the same, except that p and n have the positions swapped. So when I first see this expression, the first thing that I want to do is to give some natural constraints, some natural bounds on n and p. So because it's an integer and n and p are positive, so it's actually a positive integer, I'm going to say n to the p plus 1 is at least p to the n plus 1. I do not want to introduce a constant multiplied by p to the n plus 1, something like that, because it's not terribly useful. Now, given this inequality, I will have n to the p is greater than or equal to p to the n. And I'm going to take log on both sides. Then p log n is greater than or equal to n log p. And I'm going to divide and move n and p to the other side. And I have log n over n is greater than or equal to log p over p. Now, given this kind of inequality, I'm going to consider a function which is log x over x, where x is positive. And I'm going to take a look at how this function behaves as x increases. So apparently, I'm going to use calculus, the quotient rule, x squared, and then x times 1 over x minus log x over x squared, which is 1 minus log x over x squared. So I know that this function is going to decrease when x is greater than e. And in particular, starting from x equals 3, because we're working on integers, this function will just keep going down. So I can say that when p equals 3, or I should say when p is at least 3, I can already say that p is greater than or equal to n, because of the fact that this function is decreasing, starting from e. So this motivates me to split this problem into two cases. The first case is that p equals 2, and the second case is that p is greater than or equal to 3. And in this case, I know that I can also assume that p is greater than or equal to n. So now I'm going to start the problem. These are the drafts. So consider function therefore I should say that I should erase this line. So I have this formally divide into cases. So first I have p equals 2, then again I have to investigate the relationship between n to the p and p to the n. And now it becomes n squared and 2 to the n. Apparently, when n is 4, they will be equal. And starting from n equals 5, 2 to the n is going to be greater than n squared. And so we won't have that kind of solution. But I have to prove this first. Claim that when n is greater than or equal to 5, 2 to the n is larger than n squared. Indeed, proceed by induction. Or I say perform induction on n. When n is 5, 2 to the n is 32, greater than 25 equals n squared. So take. Assume that two to the k is greater than k squared for some k greater than or equal to 5. Then 2 to the k plus 1 is 2 times s. And this is obviously greater than k squared plus 2k plus 1, which is k plus 1 whole squared. So claim true by induction. So we know that there's going to be no solution when n is greater than or equal to 5, because what we want is n squared to be greater than or equal to 2 to the n. So we know that, therefore, n must be at most 4. Now, we've limited the number of possible cases from infinitely many to finitely many, and we can test them one by one. So, by trial and error, p must be 2 and n must be 4. And this holds because 2 to the 4 is equal to 1. Now, that's the first case. Now I go to the main case, which is that p is at least 3. Now, while we're looking at this expression, I'm going to pick q, pick prime q minimal, such that q divides p plus 1. Okay, this is very important. Now, because p is greater than or equal to 3, we must have p to be odd. So p to the n plus 1 is even. Now, for n to the p plus 1 to be divisible by an even number, n to the p plus 1 itself must be even as well. So n is also odd, forced to be odd. So because we have p to the n plus 1, where n is odd number, we know that p plus 1 should divide the denominator. And so if I pick a prime q, a prime factor q of p plus 1, this prime factor q should also divide p to the n plus 1. And hence, it should also divide n to the p plus 1. Note that q divides p plus 1 implies q divides p to the n plus 1 implies q divides n to the p plus 1. So n to the p congruent to minus 1 mod q. This is interesting because then we'll have n to the 2p is congruent to 1 mod q. We have found a number so that n to the power of that is 1 mod q. And note that q is a prime here. So now I'm going to consider the order I should write that as order of n mod q, which is the smallest integer, say smallest positive integer such that n to the power of that is congruent to 1 mod q. Or this term, order of n mod q, is a very interesting thing because once we found the order, we basically have obtained the entire sequence of powers of n mod q. For example, if I'm going to say consider 2 mod 7, then by a Fermat's-Little theorem, we can say that 2 to the 6 is congruent to 1 mod 7, but in fact, we don't actually need 2 to the power 6 to get to 1 mod 7. 2 to the 3 will suffice. So, and actually, the order of 2 mod 7 is 3. So that means we only need to find the first three powers of 2 to generate the whole the entire sequence of powers of 2 mod 7, which is 2, 4, 1. And once we reach the number 1, we know that we simply have to repeat this block again and again and again, and so on. So order is very important. So we know that n to the 2p is congruent to 1 mod q, and so we know that the first 2p powers of n should be multiple blocks of powers of n that would reach from n to the 1 up to the order. So in other words, the order must divide 2p. And it's special because p is an odd prime and it divides 2p, so there are actually very few possibilities. This order could only be 1, 2p, or 2p. We only have 4 possible cases. But one very important thing is that n to the p is congruent to -1 mod q. So we cannot have factors of p to be the order, or else it will violate this statement. So for example, if n is already 1 mod q, then n to the p should also be 1 mod q. But q is at least 3. In this case, q is I somehow forgot to make an assumption. Thanks to the checking. Is that I have to first assume that q is at least 3. So for example, in this case, I have to assume that q is at least 3, so I can keep moving. Now, having this assumption, I can eliminate the cases 1 and p. Eliminate this because n to the p is congruent to -1 mod q. If n to the p is congruent to 1 mod q, it contradicts q is at least 3. So the order can only be 2 or 2p. Now, however, we know that by the Fermat's-Little theorem, n to the q minus 1 is congruent to 1 mod q, and we know that q is a prime factor that divides p plus 1, and so obviously q must be smaller than 2p, not to mention q minus 1. So by minimality, the order cannot be 2p. and the only choice remaining is 2. This order must be 2, and so n squared congruent to 1 mod q. And we know that this is the order, so n cannot be 1 mod q, and what it could only imply is that n is congruent to -1 mod q. So that's what we have when q is at least 3. Now, of course, it's kind of this result is kind of incomplete because what will happen when q is 2 then? We have to consider it separately. So, but very fortunately, because we're working on mod q, when q is 2, we're simply looking at the parity, whether n is odd or even. So when n equals to 2, as n odd, of course we have n congruent to -1 mod q as well. So therefore, n is actually congruent to -1 mod q at all times. Now the next part that I'm going to show, the next result that I'm going to show is that we don't simply consider prime factors of q plus 1, but we consider the entire prime power. Say, what do we mean by prime power is that, for example, if I'm looking at the number 630, so I know that 3 is a prime factor of this, but in fact, I can raise this power of 3 to 3 squared. So I'm not just considering mod 3, but I'm considering mod 9, just for this example, I mean. So I'm going to consider q to the k, where k is maximal and q is prime, such that q to the k divides p plus 1. And using similar argument, similarly, we know that q to the k would divide n to the p plus 1. Now note that n to the p plus 1, we're going to make use of the fact that p is odd, and factorize this, is n plus 1 times n to the p minus 1 minus n to the p minus 2, and so on, alternate plus or minus signs, and at the end you should get plus 1. So altogether there are p terms in this bunch. Now, this part, we actually don't even have that to be congruent to 0 mod q. It does not contain any prime factor of q at all. So it's congruent to -1 to the p plus p minus 1 minus -1 to the p minus 2, and so on, plus 1 mod q, which is actually p mod q, and of course it won't be 0, right? Because q divides p plus 1. So, which is not 0, just what we want. So we know that this q to the k should only divide n minus 1, but not the yellow bunch. Given that it divides into the p plus 1, it would divide n plus 1. Now, the miraculous thing is that when I assume that q to the k divides p plus 1, I have q to the k dividing n plus 1. And this q is arbitrary. So in fact, I'm actually looking at all the prime factors, okay, all the prime power factors of p plus 1, and they would also divide n plus 1. So combining, we know that p plus 1 actually divides n plus 1. So in this case, we must have p is less than or equal to n. But we also have n to be less than or equal to p. That is from our very first inequality all the way up before we even started the formal proof. It should be here. So when we have both inequalities, we know that in this case, when p is at least 3, the only thing that could happen is that p equals to n. So we have two groups of solution. One is just a single order pair, which is 2, 4, and the other parts of the solution, other solution sets are all just equal prime numbers where p is an odd prime. So therefore, 2, 4 and p, where p is an odd prime. Oh, of course, I forgot to check, is that not just 2, 4, something missed again, is that both p and n equals 2 will also work. So altogether 2, 4 and 2, 2 and pp as well, or I should rewrite that as just where p is any prime. Checking. When p equals n, then p to the n plus 1 equals n to the p plus 1, of course take. When p equals 2, n equals 4, again they are equal. So they are the only solutions. So yay, we are done. I hope you enjoyed the video. Feel free to suggest any alternatives in the comments. If you like my videos, make sure to subscribe to my channel right now. Thank you for your support. See you next time.